I want to clarify a few things on homework number 1 for your load analysis. Probably it will simplify and make your life easier. First thing is when uh, you're allowed to make any assumption you want. Okay. Uh, let's go back to step 2 of your 6-step problem solution approach. You're allowed to make any assumption. So given that your load in one of the cases was given here at the tip, you can say, I am going to assume that the load is actually given right there at the centroid, okay, without having to place a moment. That's completely valid approach, completely acceptable. Okay, so it was not meant to be a trick. It was meant to you just use the assumption and you do that. That was the intention. When we do in engineering, many times we want to do a hand cal, we need to be quick, we need to be fast, and this is how we do it. Second point I want to explain in your homework is uh, you got your case right, and yes, your load is kind of defined all over the domain. Okay. However, we are only interested for case number 1. We are only interested in this part here. Okay. So just remember that everything that we have is in the positive y. So you can use my equations. So what you have to do is you have to keep in mind uh, that your equation q of x that was given is going to be only applicable L, X, L, right? Because it's only valid for this region here. And then what you have to know is that in your notes, I put my loads in this direction. So regardless of what happens, and you might end up with something funky, doesn't matter. You have to go as a minus q of x. So the expression I gave you in the table will be minus times whatever is there. Okay. So this is clarification number 2 in terms of the loads, how the loads are actually working. Number 3, this is like a counterbalance torque. Okay, the torque that you have here in the middle, changing this, the torque that you have here is a counterbalance torque for all the torques that are going to happen here. And I am not sure the direction of this. If the direction is this direction, then this will go in the opposite direction. If the direction was opposite, if the direction was this one, then this torque will actually go in the opposite direction, okay? And you're going to assume that the torque is applied at x equal to L over 2. It's right in the center, okay? Fourth clarification that might be very helpful. When you are finding, after you resolve everything about the centroid, and you want to find your reaction loads, to make your life a lot simpler, and you want to find what is the total load applied here, okay? The total load is nothing else than the total integral L over 2 to L py d of x dy. This is the total resultant load. So you know the load is going to act somewhere here maybe. You don't know where, but the resultant, the value of that load is that. So if I want to find the first equation would be ry1 plus ry2 plus integral L over 2 L py dx d of x is equal to 0. Now, note, again, this will be minus q of x. Okay, don't forget that. The minus is there. So then you have one set of equation. Now you need a second set of equations. Second set of equation will be a moment equation. To have that moment, let's go to the next slide. Or let me call this A, let me call this B, and we want to find the moment. To find the moment, what we're going to do is, let me change the colors. So you need to know where that load is located, right? You need to know that from this location right here. So then maybe you can take a moment there, and then you have RY2. So in order to do that, the easiest way to find the centroid from here to here is just using the fact I want to know where the centroid is. I have x, the area, divided by my total area. Okay, so if you just consider the case of an arbitrary curve, and I want to find the area, this will be nothing else than dx, okay? And this is the curve py that I'm looking for, okay? So your equation then, let's suppose, let's leave it like that. So then this will be integral L, oops, okay? This is the same thing as the integral L over 2 of L, x times pyx d of area, dx, and integral L over 2L at pyx d of x. Okay, so if you solve this, this will basically give you a number, and that number is your x bar measured from here to here. This is your x bar. You will have to add L over 2 to get this total distance. Okay, that's one way. This is the easiest way to do it. So you can find this for any arbitrary load. That will be very helpful. Okay, and then clarification number 5. Clarification number 5, for this particular method that I use in the book, the method is very, very general. So suppose I had a point load there, and I had your distributed load here as well. Okay, so when you do this, as you should know by now, you need 2 section cuts, one here, one there. And before you start, you need to make a section cut right here at x equal to 0 plus. Okay, that section cut is, if you have this, it's going to tell you the value of V1 at 0 plus. Okay, that is the value that you're going to use in your equation when you go, this is equal to V1 0 plus minus, this is 0, so 0 goes there, to x py psi d psi. And want to clarify this for a moment. This psi is nothing else than if p of x, as an example, okay, just an example, was equal to something like this, p psi, you basically take the same equation and you replace it with psi. Okay, and then that equation, you place it there. And as I mentioned in class, it's just to avoid confusions there. Okay, so let's go back. Now, then you're going to make another section cut here, And that section cut is going to look, oops, apologies. You're going to make another section cut right there, okay? And that section cut is going to look something like this. Let's suppose I have a load P applied there, have a load P. On this side, because our sign convention, we know this is V2 at L over 2 plus. We know that this side, this has to be our sign convention, V1 at L over 2 minus. Okay, so when you're doing this problem, and you want to find the value of this guy, is nothing else than using this, okay? Using this, evaluated V1, evaluated L over 2. That will give you this value here. This is the value that we need. So what you do is V2, L over 2 plus, okay, minus Vy1 L over 2 minus P is equal to 0. Then you solve for this. Okay? Once you solve for that, then you're going to go and you find V of x is equal to V2 L over 2 plus minus, again, L over 2, then L over 2 goes there, x, py, x, d of x. So what you have basically done is this value now already includes this. Okay, and step number 6, for sanity's sake, you can make a section cut at the end, and if you have a load there, let's call it P2, and the value there, Vy2 at L minus, then the value should be such that V2 evaluated at L has to equal to P2. Okay, otherwise there's a mistake somewhere. These are a few clarifications. Especially this part, I think, will help you with simplify your problem a ton. And just be systematic with the approach. Don't get so caught up with this torque. The torque is just a balancing, counterbalancing torque. How to find the total value of this is a lot easier by simply taking a full integration. And to find where the location applies, just do a simple integration as well. Okay, so I'm hoping that this extra clarification is of help.